Assalamualaikum and a very good morning I bid to all panels. We are from EH2208OO would like to present to you regarding our project entitled Production of 10,000 metric tons of bioethanol per year. These are our agendas for today. First of all, let us make a recap of Design Project 1 regarding the process details for bioethanol production. Equation 1 shows the main chemical reaction for fermentation process in our plant. Sucrose reacts with water to produce ethanol and carbon dioxide with the help of yeast, which act as a catalyst in this process. The process is in fed batch mode, where DAP or diammonium phosphate, which is an essential nutrient for the yeast, is being fed intermittently into the reactor during the process. Referring to the PFD, the green box is where mixing, fermentation, scrubbing, and also centrifugation processes occur in batch mode, whereas the red box is where purification occurs continuously. Now, let's move on to the control system in fermenter FR101. The objectives are to control flow, level, temperature at 30 degrees Celsius, pressure at 1 to 1.1 bar, and lastly pH at 4 to 5. The control strategies are ratio control for the nutrient flow and also feedback control for the others.
My name is Nuriana Shamim binti Misbah, and I will continue with the scrubber. There are four main objectives that need to be controlled. First, to control the flow of the scrubbing liquid that enters at top inlet stream 9 by using feedback controller at 33,061.273 kg per batch. 2. To control the flow of the carbon dioxide and ethanol that enters at bottom inlet stream 8 by using feedback controller at 26,532.657 kg per batch. 3. To control the level of the liquid hold up at the bottom part of the scrubber by using feedback controller to avoid from the flooding to occur. And the last one, 4. To control the pressure of the scrubber at 1 bar by using feedback controller. Next, I will pass to Eza.
For process control at centrifuge, the objective is to control the flow and level in the equipment. Referring to the table, the flow can be controlled by adjusting the inlet stream, while the level can be controlled by adjusting the outlet stream.
The objective of process control and instrumentation for the distillation column is to maintain the level column, to maintain temperature 80 degrees Celsius in the column, to maintain the pressure of 6.1 bar in the column, and to maintain amount of external reflux ratio and level in reflux drum. All the objectives were controlled by using feedback control.
Assalamualaikum and good morning. My name is Nolokman Hakim bin Anwar, and now I will present about the process control for molecular sieve. Here we have two objectives, which is to control pressure and temperature by using feedback control strategy. The pressure will be controlled at 1 bar and the temperature will be controlled at 100 degrees Celsius.
The overview of FR101. The inlet consists of sugar syrup, yeast, and also nutrient which is being fed intermittently into the reactor as I mentioned before, whereas the outlet consists of carbon dioxide, dead yeast, and also ethanol. There are many crucial parts in designing a bioreactor. Number 1, the type. For FR101, a fed batch stirred tank is being used. Number 2, size and arrangement. According to Norman et al., a typical size for industrial fermenter is between 50 to 1000 meter cube. By using mass flow rate and density to find volume, it has been found that the working volume for our fermenter is approximately 243 meter cube. Even though the volume is within the range of a typical industrial fermenter, but it is believed that smaller fermenter is more economical and the minimum number of fermenter for parallel arrangement is 4. Therefore, we chose 4 fermenter for our plant. And lastly, the agitation system, which includes baffles and also impellers. The most common impellers used is Rushton impellers. This is the AutoCAD design of FR101. It is a cylindrical column with ellipsoidal heads that has a total height of 9.2 meter and an outer diameter of 3.1 meter. It is made of stainless steel type 304 and consists of 3 Rushton impellers and 4 baffles.
Today I will be presenting about the wet scrubber design. There are many steps for designing the pack wet scrubber. However, we will go through 2 major steps, which are chemical and mechanical design. Now, what's with the pack wet scrubber? Pack wet scrubber is commonly used for the gas absorption, which the scrubbing liquids will spread over the packing material in order to provide a larger surface for liquid gas interaction. For the packing material, I chose the interlock saddle ceramic because it is suitable for the corrosive liquid. For selecting the packing size, at first I took 1.5 inch in order to determine the tower diameter. However, after I go through some calculation, the ratio of the diameter of the tower to the packing size is 13, which is less than 15. However, I changed the packing size to 1 inch, and finally I got the ratio 40, which is way larger than 15. Therefore, it is acceptable in the heuristic. Finally, the diameter of the tower is 1 meter. Next, I determine the height of the pack wet scrubber using Cornell's method and Ondas method. By comparing these two values of gas phase overall transfer unit, or HOG, for the Cornell's method is more larger than the Ondas method. Therefore, Cornell's method will be chosen. After some calculation, I get the overall height for pack wet scrubber is 5 meter, as you can see in the figure there. 3 meters height for the packing, 0.7 meter height for the liquid level, and the remaining are for the liquid nozzle, distributor, mist eliminator, and the head. For the same thing, I will check the heuristics for the pack towers. The ratio of L over D for this wet scrubber is 5, which is in the range to 2 to 30, which is acceptable. Last but not least, this is our final look of pack wet scrubber after going through the 2 major steps. As you can see at the cross-sectional view there, it is countercurrently flow, which the scrubbing liquid or the blue arrow introduced at the top of the tower using sprays and flow downward over the packing material, while the contaminated gases or the red arrows there is enters at the bottom of the tower and flow upwards through the packing materials.
Okay, next, I will be presenting my part in Chapter 9, which is the design of centrifuge. Centrifugation is a process of separating materials with a different density. This process allows small particles or cells to be separated from liquid. Centrifugation can be classified into 2 types of mechanism, which are filtration and sedimentation centrifuge. According to Advanced Biotechnology textbook, sedimentation centrifuge is suitable for the separation of yeast cells in ethanol production, and due to fine particle size of yeast, the sedimentation centrifuge was chosen. The selection of centrifuge can be classified according to its particle size, as referred in the slides. The particle size of Saccharomyces service says is commonly in range of 5 to 10 micrometer, and in this bioethanol plant production, the particle size is assumed to be 5 micrometer. Based on the figure, the particle size of yeast falls in range of decanter, nozzle, solid ejecting, and also solid retaining type. Other than the particle sizes, the selection of centrifuge can also be done by the calculation of percentage solid content. Based on the calculation, the percentage of solid content falls in range of solid ejecting and also decanter types. Comparing these two types of centrifuge, decanter has been chosen due to its wide range of capacity. Next, in slide, it shows the detailed design of the centrifuge with a line dimension of 2340 mm with a pond diameter of 356 mm.
Distillation is a process that separates two or more components into an overhead distillate and bottom. Many types of distillation can be found in the industry, such as packed bed column, free column, vacuum tower, triple column, and multi-effect distillation column. The number of tree in the tree column is depend on the number of stages. It has better liquid distribution and can handle high liquid flow rate. On the other hand, it is suitable for the high capacity plant. The shift plate is chosen to use in this distillation column because it has low maintenance cost, easy to clean, and relatively inexpensive compared to bubble cap and puff tray. Based on our bioethanol plant, distillation is used to purify the ethanol from the mixture of ethanol and water. This distillation column C101 is a continuous column. The feed stream is fed at 80 degrees C and 6.1 bar. The top product of the distillation column lives at 80 degrees C and 1 bar, while the bottom product lives at 100 degrees C and 5 bar. The design distillation column 40 meter in height with 1.7 of diameter. Our distillation column has 21 number of stages and the feed is at 15 stage from the bottom of the tower. Therefore, in our distillation column, we decide to use 0.5 meter for plate spacing as it between range of plate spacing for diameter above 1 meter. We also have decided to use carbon steel as the material of the vessel. It is cheap and available in a wide range of standard form and size. The corrosion allowance of 3 ml will be used as an additional thickness of metal added to allow for a material loss by corrosion, erosion, or scaling. The vessel thickness is 8 ml. A 90 degree cylindrical skirt made from carbon steel with a thickness of 11 meter is used as the vessel support.
Okay, now for the molecular sieve design. Molecular sieve column are used for ethanol purification, which is up to 99%. Where ethanol will pass through the bed, then the desiccant will absorb the water molecule. In this design, bit form of synthetic zeolite 3A, which is aluminosilicate mineral, is used as the desiccant. As you can see on the slide, there is the operating condition which is regeneration temperature, absorption cycle time, regeneration cycle time. These three data is very important before starting your chemical design. There are also one formula which is used in this calculation to determine the bed diameter of the molecular sieve column. Okay, now we move to the mechanical design. On the slide, there are some of the summary of mechanical design that have been calculated. This slide shows the AutoCAD drawing of the molecular sieve column with a diameter of 1.524 meter and height of 12.22 meter. Okay, now for the economic analysis. For the estimation of capital cost, feed capital investment has been determined, which is around 44 million ringgit. In the estimation of manufacturing cost, raw material cost, utilities cost, waste treatment cost, and operating labor cost have been calculated. Then, cost of manufacturing can be determined by using those costs, which is around 66 million ringgit. Now we move to the profitability analysis. There are a few assumptions that have been made. First is the project life is 13 years. Second, the time for construction is 2 years. Next, the price of raw material and the product is constant throughout the project life. Next, the distribution of fixed capital investment is 60% for the first year and 40% for the second year. Last, depreciation is 5 years using modified accelerate cost recovery system method. The revenue from sale is 80 million ringgit per year and the working capital is around 8.8 million ringgit. On the left side of this slide presented about the non-discounted cash flow, while on the right side presented about the discounted cash flow. Both graphs show the cumulative cash flow for both non-discounted and discounted cash flow. For non-discounted cash flow, the cumulative cash position is about 96 million ringgit and the cumulative cash ratio is 1.702. The payback period is 3.61 years after startup and the rate of return on investment is 16.66%. Okay, now we move to the discounted cash flow. The interest rate is assumed as 10%. The discounted payback period is 5.215 years after startup. The net present value is about 19 million ringgit and the discounted cash flow rate of return is 15.83%, which means that it will have zero net present value if the interest rate is equal to 15.63%.
In Chapter 11, under the plant safety and layout, hazard identification, risk assessment and risk control, or in short HIRAC, is functioned to identify all the factors that may cause harm, to consider the chances of a risk and its severity, as well as to enable the employee to plan, introduce and also to monitor the preventive measure. In the HIRAC form as shown in the slides, it indicates the possible hazard that may occur in our plant and ways to overcome it.
The objective of HAZOP is to identify possible deviation from normal operation and to ensure that appropriate safeguards are in place to help prevent accident. The first column will represent process parameter such as flow and level. The second column will represent guide words such as less, more, high or low. The next column is possible causes, possible consequences and action required to help prevent accidents. Because of time constraint, I just presenting HAZOP for our first unit operation in PFD, which is mixer. Based on the table, possible causes for no flow scenario are when there are pipe or tube blockage or have a problem with a supply shortage. In consequence, our mixer will dry out, delay in supplying to the next unit, and the worst that the mixer will shut down and fail to operate. To prevent it, we need to do maintenance checkup regularly and install flow alarm low for the equipment. Next, possible causes for more flow scenario are when there is a failure in the control valve or the control valve is fully open. As a result, flooding and mixer structure blockage. To prevent it, we need to install a flow alarm height for the equipment. Less inflow will have a similar possible causes, possible consequences and action required as no flow. Moreover, the possible causes of height level in the mixer are output blockage. In consequence, the mixer will be flooding in with the mixture, while possible causes for low level is inlet pipe leakage. As the result, the mixer will delay supplying to the next unit. The best action for both high and low level is check maintenance regularly and install a level alarm for high and low level. Emergency Response Team (ERT) is a special team that responds to general and localized emergency to facilitate personnel evacuation and safety. Everyone in the company plays such an important role when emergency happens. The assistant manager of the affected plant will act as incident controller until the manager or head of the department arrive. The manager of the safety and health department with their assistant will monitor the overall safety handling of emergency, while the manager of the security service will leading the arrangement of the effective security near the affected area. Furthermore, the factory medical officer will immediately contact the main incident controller for the information about the incident and will render the necessary treatment at the first aid center. Last but not least, the HR manager will contact all deputy as per the instruction of the main incident controller.
Lastly, plant layout can be defined as an optimum arrangement of an industrial facilities which include the operating equipment, personnel, storage handling, and also other supporting services. And as in our bioethanol production plants, the plant layout have been provided in a 2D and 3D view as referred in the slides.